Hi, this is Maggie. In this video we're going to talk about vector motion. This program called batterycollector.py randomly generates a location of a robot and two batteries. And then, after 2 seconds, moves the robot to the closest battery. The distance formula is used to calculate which battery is closest to the robot, and then the robot simply jumps to the new location. The program would be more interesting and realistic, if you can call this at all realistic, if the robot moved toward the battery until it reached the battery, rather than simply teleporting to the exact battery location. This representation is figure 9.4 from the text, but with robot and battery images superimposed over the points. Suppose we want our robot to move toward the battery. How do we do that? To reach the battery, the robot will have to move in the right direction along this hypotenuse at a particular speed. Together, speed and direction are referred to as velocity, and we can represent velocity with a vector. A vector is a mathematical object that has both magnitude, or size, and direction. In figure 9.5 of the text, we see the line between the 2 points shown as a vector. The vector doesn't have a location on the screen. It is representing, again, a velocity. So it is representing the direction of motion and the speed. One way that can be represented is as an ordered XY pair. If the robot moves 8 pixels in the X direction and 6 pixels in the Y direction, then it will have moved to the battery. Another way the vector can be represented is as an angle and a speed. So if the robot moves 10 pixels at an angle of 36.87 degrees, then it will reach the battery. Now, of course, this is exactly what we don't want our robot to do. We don't want it to jump directly to the battery. Suppose we shorten our vector, but keep the angle the same. So suppose, for example, I use the angle speed representation. So I keep the angle the same, and I shorten that length, or speed, to 1. Then the robot will take 10 steps to reach the battery. Or maybe I want to move it a little faster. Say 2. Then it will take 5 steps to reach the battery. What I want to do is calculate a unit vector. A unit vector is a vector that points in the same direction as the longer vector, but has a magnitude or length of 1 unit. I can then multiply the unit vector by speed to get a vector of the length that I want. Let's modify the battery collector program to have the robot move toward the nearest battery. We'll call it batterycollectormotion.py. I think I'll leave the code that randomly moves everything at 4 seconds, but I'm not going to wait 2 seconds and then have the robot jump to the nearest battery. Each time through the game loop, I'll increment the counter because I'm still using it for the 4-second test, and I'll calculate the distances. So I use the distance formula to calculate distance 1 and distance 2, and I compare them. But then, instead of teleporting the robot to the closest battery, I'll have it move toward the closest battery. So I will need to calculate a unit vector, which will be the amount the robot should move in the X direction and the amount the robot should move in the Y direction, so that the total distance moved is 1 pixel. And I'll multiply that by a speed factor so the robot gets at least somewhat close to the battery before everything changes at 4 seconds. So here's how I do that. I'll take battery 1x minus robot x and divide that difference by distance 1. If we go back briefly to our drawings and I superimpose my unit vector over my long vector, you can see it's pointing in the same direction, but the distance that it represents down and to the right is just a small proportion of the longer distance down and the longer distance to the right. What I need to do is calculate the sides of this tiny triangle. So I know the dx and dy that I need to add to the robot's xy coordinate to move it a step. So I'm going to basically scale down my dx and dy, and here they are 8 and 6, to whatever is the right number for this tiny triangle. And I do that by taking the distances and dividing by 10, because my scale is 1/10, or 1 over the distance between the points. And so, back in the code, I'm going to add that dx to the robot's current x, and then repeat that calculation for y. And then repeat it using the second battery's coordinates, if that battery is closer. Now I'm going to annotate a variable called speed. And we'll try setting that to 2, and I'll multiply each of these amounts by speed. Before adding to the robot's xy coordinate so that it moves a little bit faster. That may or may not look right, and we can adjust that. One other thing I should do is check that the distance is not 0 before dividing by it, since that would cause a crash. If the robot actually reaches the battery, we don't want the program to crash because the distance is 0. Okay, let's run that. And the robot moves toward the closer battery, and I think the speed's okay. When he manages to get close to a battery, he wobbles a little bit, and that's because he's moving slightly past the coordinate of the battery, and then moving back, and then past, and then back. What we could do is write some code to check if we're within a threshold of speed pixels, and set the robot's coordinates to exactly the coordinates of the battery when that happens. So that is an introduction to vectors, what they are and how we can use them to calculate a unit vector and move an object in our game in the direction of the vector at a speed that we specify. Practice with this concept. Take your robot battery collector program and rewrite it to have the robot move toward the battery slowly, as we've done here. Keep practicing with it until you can write the code without looking at this code and you know what every line of code does and why. Once you have that down, you're ready to move on.